Okay, welcome back. Now I'm going to do examples having to do with entropy in thermodynamic processes. Entropy in thermodynamic processes. So let's assume that there is 10 moles of gas. Initial temperature is going to be 300 Kelvin. So that's about room temperature, right? And then the initial volume is going to be 0.1 cubic meter, which is going to be 100 liters, right? And we can also calculate what its initial pressure is, right? From this, the ideal gas law. Okay, so then let's say I am heating the gas with different methods, right? Let's find out the change in entropy of the gas. So I'm starting here with V initial is 0.1 cubic meter. P initial we don't know, but we can solve for that, right? So P initial, V initial equals nRT initial. So then D initial is 0.1. The 10 moles of gas, 8.314. The initial temperature is 300 Kelvin. All right, so since 101,000 pascals is 1 atmosphere, we can say this is about 2.5 atmospheres, right? 2.5 times atmospheric pressure. So now what if I double the volume at isobaric process? The final is 0.2 cubic meter. Right? And then I double the volume and I ask, what's the change in entropy of the gas? Okay? So change in entropy in an isobaric process. So remember, change in entropy is dQ over T, right? So then, what's the dQ? So the dQ in an isobaric process is going to be the work done by the gas plus change in internal energy of the gas, right? The work done by the gas is going to be nR delta T. I'm going to say nR dt, right? The change in internal energy of the gas is going to depend if it's a monatomic gas, diatomic gas, or polyatomic gas. So that's where that comes in. So there is no general answer I can put here. So if it's a monatomic gas, it's going to be 3/2 nR dt, right? If it's if it's a diatomic gas, it's going to be 5/2 nR dt. If it's a polyatomic gas, it's going to be 7/2 nR dt, right? So then when I combine this, I'm going to get what? So this is true if this is a monatomic gas, right? Now, the other way to generalize this is to say that 5/2 R is the CP value, the specific heat at constant pressure. So since this is being done at constant pressure, we can just say NCP dt, right? So we can say delta S is equal to NCP dt over T, right? So then if I integrate that, that's going to give me the total change in entropy of the whole stage, right? So it's going to be delta S is going to be NCP, and then this is going to be ln of T final over T initial, okay? So then, how can we do this? Well, if it's a constant pressure, we know that P is equal to PV is equal to nRT. So if the pressure is constant, we can say V over T is same as V over T. So V1 over T1 is equal to V2 over T2, right? So if the volume is doubling, the temperature is also going to double. So whatever the volume is doing, the temperature is doing the same thing, right? So we can also say this is equal to NCP ln of V final over V initial. So you can basically use either equation for change in entropy in a isobaric process, NCP ln T final over T initial or V final over V initial. So in this case, since V final is given to us, we can just take the ratio of that. So that's going to be 2, right? So then it's going to be delta S is going to equal NCP, so the number of moles is N, right? And then let's say this is a monatomic gas. So if it's a monatomic, the CP is going to be 5/2 R, right? And then we're going to have ln of 2. Okay? Okay, now that is of course if if you're going this direction. If you went the other direction, the change in entropy would be negative, right? Okay, now how about if you were to, instead of going this way, if you were to go down to half the pressure, half the initial pressure, what would be the change in entropy now? Okay, so now it's going to be negative because you're decreasing the pressure. If you went up to twice the pressure, the change in entropy would be positive. So once we know how to do the down, we can also do the up. It doesn't really matter, right? So then let's erase this since we have the answer there already. Okay, so what's going to be the change in entropy in isovolumic? Change in entropy is going to be dq over T. Okay, dq is equal to W plus delta E over T. Right, so what's the work done? Isovolumic is 0, right? Isovolumic, the work done is 0. So then you have just change in internal energy. Okay, change in internal energy depends if it's a monatomic gas or diatomic or polyatomic. So now we put here NCV delta T, right? NCV delta T over T. All right, so that's the only thing that changes. And then we integrate that. And then we get the total change in entropy is going to be NCV ln T final over T initial. Okay? So for this one was at constant pressure, isobaric. For isovolumic, it's going to be NCV ln T final over T initial. But since it's isovolumic, we could also do P final over P initial, right? So isovolumic, the volume is constant, right? So then we can say pressure over temperature is equal to pressure 2 over temperature T2. So the ratio of the temperatures is the same as the ratio of the pressures, right? So then we could say delta S is NCV ln P final over P initial. So these two apply for isobaric, isovolumic. These two apply for isobaric. Okay. So then if we went down, it would be negative ln of 2. Right. So delta S would be N. CV would be 3/2 R. Okay, ln of, since we went down, the ln of 1 over 2, or we can say negative ln of 2. The entropy change is going to be negative. So delta S, negative 10, 3/2, 8.314 ln of 2. Okay. So then 86.44. Okay. So it's going to be smaller because instead of 5/2, it's now 3/2. So it's going to be a ratio of 5/3 smaller than the 144, right? So 86.44. So then we can say negative 86.44 joules per Kelvin. Okay. If we went up to twice the pressure, it would be positive 86.44. Okay. Now how about if we went isothermally? We went down this way. Okay, isothermally now. How do we calculate the change in temperature? So now if we doubled the volume, the pressure would naturally half, keeping the temperature the same, right? So this would be half the pressure. So this would be an isothermal, right? So then how do we calculate delta S in isothermal? So we have delta S is equal to dq over T. So this is actually should be a differential. ds is dq over T. dq is equal to W plus delta E over T. In isothermal, delta E is 0, right? And the work done is equal to what? P dV, right? P dV over T, right? So then what is that going to be? Well, from this we have here PV is equal to nRT, right? So in our case, we have isothermal, so this is not changing, right? So P is just equal to nRT over V, right? So we can replace P by nRT over V, nRT over V, dV over T, right? So remember, the work done is going to be pressure times dV, but the pressure is changing. So the pressure is changing, nRT over V, in other words, pressure is changing as 1 over the volume, right? Then you're multiplying that by dV over T, but the temperature is not changing, right? So this T cancels this T, right? So you basically get ds is equal to nr dv over v, right? And then you integrate that. So delta S is equal to nr ln of v final over v initial. So it looks like these equations, ncp ln t final over t initial, ncp ln v final over v initial. This is ncv ln t final over t initial, p final over p initial. So how is that different? Instead of ncv or cp, it's just nr, right? So the change in entropy is nr ln v final over v initial. Okay? Now this cp is 5/2 r for monatomic gas. So the change in entropy for an isobaric process is a lot more because the molecules actually start agitating and the temperature of the gas increases. In an isothermal process, we're letting the gas expand, we're putting in heat, but we're letting it expand and the molecules are not speeding up at all. If they're not speeding up at all, their entropy should not increase as much. The only thing that's happening is the volume is increasing. If the volume increases, there is missing information to where they're located, but since their speed is not changing, right? If the temperature is not changing, that means their root mean square velocity is not changing. So if their root mean square velocity is not changing, that means our missing information about how fast they're going is not changing. So the uncertainty about how fast they're going is not changing, only where they're located is changing, right? So since the volume is increasing, the ln v final over v initial, that should increase their entropy, but their speed is not changing. So the change in entropy should be smaller than for isobaric process, right? So then you have here nr ln. So this is the smallest change in entropy. Isovolumic is the middle. Isobaric is the most. Okay. Now why is isovolumic less than isobaric? Well, because in isovolumic we're keeping the volume the same, so their uncertainty about where they're located doesn't change, but the uncertainty about how fast they're moving is changing. You see here? Uncertainty about how fast they're moving. Here, uncertainty about where they're located. Isobaric, uncertainty about where they're located and how fast they're moving. The volume is increasing and they're also speeding up. So two pieces of information is changing: where they're located in terms of volume and how fast they're moving. So the isovolumic is in the middle between the two. Okay? How about adiabatic? Definition: adiabatic is a sealed container where there's no heat exchange, and so dq is 0, right? So if we do the process reversibly and slowly, quasi-statically we call that, and we go down adiabatically, adiabatic is a more steeper curve, right? We go down adiabatically, but we always let the gas come back to equilibrium. So move it a little bit, come back to equilibrium, move it, move it, move it. No heat is coming in, exchanging. That means the dq is 0 and delta S is 0. So in adiabatic, delta S of the gas is 0 if it's done reversibly and quasi-statically. Okay? So why is that? Well, because even though the gas is expanding, so there is missing information as to where it's located, right? Oh, the gas is now occupying a bigger volume, twice the volume, but the gas is cooling down. Why? Because when it expands and no heat comes in, the gas cools down. So there's missing information is increasing as to where it's located, but because it's slowing down, there's less uncertainty about their speeds because their velocities are lower now. So we have a little bit more information what their potential velocity is, right? When the velocity of a gas is larger, the bell-shaped curve, the Maxwell distribution is wider, right? That means some gas molecules can be moving very fast, some could be moving slower. There's uncertainty about the distribution of molecular speeds. When the gas expands adiabatically, the gas cools down, and what happens? The root mean square velocity of the molecules slows down. More particles are moving at the root mean square velocity and at the most probable velocity, right? More molecules are moving with that. The distribution of molecular speeds is less, and there's more certainty about how fast the gas particles are moving, right? So the entropy of their speeds goes down. The entropy due to the volume expanding goes up. The two cancel each other, and the total change in entropy in adiabatic expansion is 0, right? Now, earlier in the theory section of entropy, I explained to you that there is something known as adiabatic free expansion, and that's when you open a certain chamber and you allow the gas to freely expand to occupy the full chamber. That's a different kind of adiabatic expansion, because in this kind of adiabatic expansion, the gas is doing work against the piston as it's expanding, right? So because it's doing work, its entropy is decreasing due to the work that it's doing. Here, because the gas is freely expanding, its entropy actually increases. Its speed doesn't go down, right? So as the gas expands, the initial temperature and the final temperature is the same, equals the final temperature. It's just that the gas naturally expands to occupy bigger volume, and its entropy increases due to the volume increase of the gas. So then in that kind of case, the change in entropy is equal to, it would be like this equation, nR ln V final over V initial. So it's the same equation as for isothermal expansion of a gas, for adiabatic free expansion. But the regular adiabatic would be delta S is 0. That's where the gas is doing work against the piston and it's cooling down. Okay? Now let's make a whole cycle. Let's see what happens. Imagine now the gas goes isobarically, then isovolumically it goes down, then it goes this way isothermally, back to the origin. Okay? So then what would the answer be? The total change in entropy of the gas. Okay? So let's make a whole cycle, this way, this way, this way. Okay? So then we already have the answer, 144.1 joule per Kelvin for the first stage. Now if you go down isovolumically, this one was 86, what would happen? Well, it would be the same answer, right? It would be NCV. So whether this isovolumic was done here or it was done there, it doesn't matter, because the equation is NCV ln P final over P initial. Well, as long as P final is half of P initial, it doesn't matter where the isovolumic is occurring. So this answer would be the same as that one, which was what? Right? And then this one is going to be what? The entropy is going to decrease, right, when going back. And then it's going to be like this. So delta S2 is in negative 86.44. Delta S1 is 144. And then delta S3 is going to be nR ln V final over V initial, which is going to be, V final is half of V initial, right? It's returning back. So that's going to be 1/2, or you can do negative nR ln of 2. So delta S3, negative 10, 8.314 ln of 2. Okay? Negative 57.63. Negative 57.63. Okay? So the total change in entropy of the gas is what? Okay, so the total change in entropy of the gas, when you add up all this, is going to be 0, right? Delta S of gas is going to be 0, because we're assuming you're doing this in such a way, such a slow way, that you return back to the same initial condition and the gas is the same initial volume and same initial temperature. There are no heat losses due to friction. That's what's called a reversible process. That means you can perform this process again over and over many times, and you can return back to the same initial conditions. Okay? So the total change in entropy of the gas is 0, right? So that should be the true. How about the change in entropy of the environment? What's happening to the environment? So barically, heat must come in from the environment, right? And then in order to do the isovolumic, you have to expel out heat. And isothermal, you're going to expel out heat. Okay? Let's say you are doing this under condition where the atmosphere's temperature is not changing. So you're doing certain things to the gas, and then the atmosphere's temperature stays constant at 300 Kelvin. Let's say it's room temperature. So the initial temperature of the gas was 300 Kelvin, and then the gas increases its temperature, right? It doubles its temperature. So since the volume is doubling, the temperature of the gas is 600 Kelvin here. Then the temperature goes back down to 300 Kelvin because you have the pressure. Then you go back 300 Kelvin. So the temperatures at the three corners are 300 Kelvin, 600 Kelvin, 300 Kelvin, then isothermally back to 300 Kelvin, right? In the meantime, the temperature of the environment has stayed 300 Kelvin. So what is the change in entropy of the environment? Delta S1 environment. So in the environment, the first stage, the environment loses entropy because it's giving heat to the gas. The gas gains entropy, right? The environment loses entropy. So it's equal to the negative Q, we can call this Q1, over the temperature of the environment. The temperature of the environment is staying 300 Kelvin, right? So delta S1 environment, how much heat comes in? Well, that's equal to, we assume this one was monatomic gas, so it's equal to 3/2 nRT plus nRT. So basically, it's going to be the total heat is going to be NCP delta T over T environment. So for since constant pressure, it's going to be the molar specific heat at constant pressure. So negative delta S1 environment, negative 10. Okay, CP is going to be 5/2 R. So change in temperature was 300 Kelvin. Then I'm dividing that by the temperature of the environment, which I'm also assuming is at 300 Kelvin. It's always staying 300 Kelvin, right? This 300 and this 300 cancel. The reason it canceled in this case is because the change in temperature of the gas was coincidentally the same as the temperature of the environment, which was, I was assuming, was already at 300. So then you're just going to get, okay? Now, the change in entropy of the gas in the second state, environment. In the second state, the gas is losing heat, so it's losing entropy, but the environment is gaining heat, right? So you are dumping heat to the environment. How much heat are you dumping? Positive, because the environment is gaining heat, right? So we're going to say that delta is to environment 10 times 3/2 times 8.314. What's the change in temperature? From 600 to 300. And then divide that by the temperature of the environment, which is 300. This and this cancel, and then you're just going to get 71 joule per Kelvin. Delta S3. So now, isothermal process, the environment is gaining heat, right? Integral PdV over T, right? And then the integral PdV is equal to nRT dV over V over T, right? So now this T over here is the temperature of the gas, right? And this is the temperature of the environment. So this is the gas temperature, this is the environment temperature. So the equation is going to be nRT gas, and then you're going to do integral dV over V over T environment. Okay, so the general equation is going to be nRT, temperature of the gas, divided by whatever constant temperature that the environment is at, times ln of V final over V initial, right? We can do here ln V final over V initial. Now, in this case, the temperature of the gas and the environment are the same, so it's actually going to cancel, right? But this would be the general way you would do whatever temperature the gas is at, and then you would divide it by the temperature of the environment, right? So in our case, what is that going to be? Then you're going to have here delta S of the environment. So the environment is gaining heat. So I'm going to write this as a positive. So you're going to have here 10 times 8.314. Temperature of gas in the environment will cancel. Then you're going to do ln of 2, right? 57.63 joule per Kelvin. Okay, now if we add up all these entropy changes, delta S environment, let's see what we get here. Negative 207 per Kelvin. Okay, this seems to violate the second law of thermodynamics. So the change in entropy of the gas when it went around was 0. The change in entropy of the environment was negative 25. So did the universe go from being disordered to more ordered? Did the universe decrease its entropy? Well, there's an extra missing factor we're not taking into account here, right? In the first step, when we poured heat to get this system going, we poured a certain amount of heat into the gas, right? So imagine the gas chamber. The initial volume is 0.1 cubic meter. To start this out, you had to pour a certain amount of heat, right? Which was the heat coming in Q into the gas, in order to increase the temperature of the gas from room temperature, which was 300 Kelvin, all the way to 600 Kelvin, to double the temperature, right? 300 to 600 Kelvin. How much heat did we have to put in? NCP delta T, right? QNCP delta T. Okay, so that's a lot of joules of energy. Now, what was the source of that heat? Did we burn some coal, right? Did we turn on the oven? Did we burn something? Did we do something? How did we produce that heat? Okay, we had to use another machine, some instrument, maybe a candle. We had to burn a candle. By burning a candle, the entropy of the candle is increasing, right? So we have to do something, some kind of flame, some kind of steam engine, some kind of source of heat that is coming in, but the entropy of that thing that is coming in is increasing, right? When we're burning the flame, we're using up the gasoline, right? So the change in entropy of that other source, which is bringing the heat, has to be at least 25.51 positive, right? So the change in entropy of the source of heat, it has to be at least 25.51 joule per Kelvin. But in reality, it's going to be a lot more than that. Maybe 50 joule per Kelvin, maybe 100 joule per Kelvin, maybe 200 joule per Kelvin, right? We're going to do a steam engine, we're going to do a flame, we're going to do a candle, we're going to use up something, and its entropy is going to be increasing, so it's going to be at least increasing by 25 joule per Kelvin. So you can see here how we can apply the law of entropy to all of these kinds of things, do a full cycle, show that the full entropy of the gas is zero, but even if the environment is negative, that means there's some source of heat which is also getting wasted, its entropy is increasing, and it's got to increase by a minimum of at least 25. So you can see now the usefulness of entropy applied to different processes, thermodynamic processes, and how to do a full cycle about it, okay? Thank you very much.